Hi students, in this video, we are going to discuss the question number 1 and 2 from first chapter exercise 1.1. Let's start to solve the questions. So the first question, use Euclid's division algorithm to find the HCF. So we have three subdivisions in this to solve. So before solving the question, let me explain you what is Euclid's division algorithm. So in class 9, you would have studied polynomials chapter, isn't it? In that we have division algorithm, yeah? That is P of x is equal to G of x into Q of x plus R of x. Here P of x is a polynomial, so everything is a polynomial, and this is dividend, and G of x is divisor, and Q of x is quotient, and remainder, R of x is remainder. The same way for Euclid's division algorithm, we write it as A is equal to BQ plus R, and R is 0 less than or equal to R less than B. Here A and B are positive integers. We have to take A as dividend, B as divisor. Okay, so these two are positive integers, and Q and R are the quotients and remainder respectively. And reminder's value always should be a whole number, and it should be 0 or greater than 0, but it should be less than the divisor. So this is Euclid's division algorithm. So using this, we are going to solve the three subdivisions. So whenever we have two numbers or more than two numbers, for Euclid's division algorithm, we can apply for only two numbers. So check which is the greatest number, that will be the dividend. So here 225 is the greatest number. So we write it here as the dividend, that is as A. Till we get the remainder of 0, we have to proceed with the algorithm. So here we are going to divide this 225 by 135. So when we divide this is 1 times. So when we subtract it, we get it as 90. So how we have to write is BQ plus R, isn't it? So here quotient is 1 into divisor is 135 and remainder is 90. As I said, you have to proceed till you get the remainder as 0. Mention that remainder is not equal to 0. In the next step, we have to write A as whatever the divisor you had in the previous step, that is 135. And the divisor will be the previous step remainder. Okay, now we are going to divide 135 by the previous step remainder, that is 90. So it is 90 into 1 times. When we subtract, it will be 45. So quotient is 1, divisor is 90, and remainder is 45. So remainder we are not getting as 0, that is R not equal to 0. Again, we have to proceed. So whatever the divisor, write it as dividend in the next step. 45 is the remainder. Here it will be the divisor. When we divide 90 by 45, 45 into 2s are 90, isn't it? When we subtract, we are getting remainder as 0. So the answer stops here. The quotient is 2, divisor is 45, remainder is 0. So we stop the step here, and the final answer will be whatever the divisor you have in the last step, that will be the final answer. That is HCF of, either you can write in word forms or you can write it in brackets. HCF of, write always the greater number first and then the smallest number equal to the divisor what you have got, and write that's the answer. So this is how we solve. Till you get the remainder as 0, you need to proceed. If you're getting remainder at first step, then that will be the final answer. Okay. So if you're noting down, please pause the screen and note down. And if you have any doubt, please post it in the comment section. And we are proceeding to the second subdivision now. So second subdivision 196 and 38,220. Obviously, the greatest number will be 38,220. We are going to divide it by 196. So 38,220 divided by 196. 1 times 196 when we subtract, we get 186, and the next number 2118, 1862, 9 times 1764. When we subtract, it will be 98, and 0 980. 5 times is 980. Remainder will be 0. In this subdivision, we are getting the answer in the first step. Quotient is 195, divisor is 196, remainder is 0. As we are getting remainder as 0, we stop here and we write the answer as HCF of 38,220 and 196 is the divisor, whatever you have in the previous step, that will be the answer, 196. You have to show this division part, the calculation part in the corresponding rough column, or you can work out in the main space, nothing problem. But this should be shown either in main space or in rough column. It should be neatly presented. So that is important. Now we proceed with the third subdivision. 867 and 255. Obviously, we have the greatest number 867. And when we divide it by 255, 3 times is 765. When we subtract it, we get as 102. Quotient is 3, divisor is 255, and remainder is 102. We are not getting remainder as 0. So R not equal to 0. The next step, whatever we had in the divisor, that will be in the dividend. Whatever we had in the remainder, that will be the divisor. So 255 and 102. Now we multiply with 2, that will be 204. When we subtract, we get as 51. Quotient is 2, divisor is 102, remainder is 51. And now we are not getting remainder as 0. So the next step will be 102, that will be the dividend, 51 will be the divisor. So 51 2s are 102, the remainder is 0 finally. So quotient is 2, divisor is 51, remainder is 0. As we are getting remainder as 0, we are stopping it here, and the divisor 51 will be the answer. So HCF of 867 and 255 is 51. This will be the final answer. And now we are proceeding with the next question. Show that any positive integer is of the form. So whenever we have the questions in form of odd and even integers, you always do this process. Either you express as multiples of 2 or you divide it by 2. Generally, whatever the number may be, if it is a 3-digit number, 5-digit number, 7-digit number, say for example 4861. When we divide it by 2, this is an odd number, isn't it? So when we divide it by 2, we get 8, 2s are 8, 6, 2 3s are 6. So we get as 1. If suppose if it is 9, we write it as 2 4s are 8. Remainder will be 1. Always, whatever the number of digits it may be, you will be getting, if it is an odd number, you will be getting remainder as 1 when divided by 2. If it is an even number, you will be getting the remainder as 0. So here the question is, show that any positive odd integer is of the form 6q plus 1, 6q plus 3 and 6q plus 5. So we try to express in terms of multiples of 2 plus 0 or plus 1, and we'll check whether it is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. So again we use the Euclid's division algorithm. A is equal to bq plus r. So we are taking the 6q and remainder we have to take, since the divisor is 6, the value of remainder will be 0 to 5. Yeah, so we have to discuss for each value of remainder. So when r is equal to 0, a is equal to 6q plus 0, So we try to express as a multiple of 2. We can take 2 as common, isn't it? So it will be 2 into 3q plus 0. That 0 is not a problem here. And now we are assuming this 3q as m. The next step will be 2 into m. We have expressed as a multiple of 2 and the remainder is 0. Therefore, 6q plus 0 is an even integer. The next step, r is equal to 1, a is equal to 6q plus 1. We cannot simplify this plus 1, so let it be as it is. For 6q alone, we try to express as multiples of 2, that is 2 into 3q plus 1. Again, we are assuming 3q as m here, so let 3q is equal to m, so 2m plus 1. That means when divided by 2, it leaves the remainder 1. That means 6q plus 1 is an odd integer. So one part we have proved. So 6q plus 1 is an odd integer. Next step, when r is equal to 2, a is equal to 6q plus 2. Overall, we can take 2 as common. That is 3q plus 1. And let us assume 3q plus 1 is m. That is, let 3q plus 1 is equal to m. We are getting 2m. That means we can write as 2m plus 0, isn't it? So now this 6q plus 2 is an even integer as we are not getting any remainder after taking 2 as common. Now, when r is equal to 3, a is equal to 6q plus 3. We cannot take overall 2 as common. But we can try to split this split this 3 as 6q plus, I'm splitting this 3 as 2 plus 1. Either if it is 3 as a whole or 2 plus 1, both means the same, isn't it? Just an alternative. And here we are combining these two terms. That is, we are taking 2 as common from the first 2 terms alone. That will be 3q plus 1 plus 1, let it be as it is. As usual, we are assuming this 3q plus 1 as m. And now we are getting 2m plus 1. Here let us assume let 3q plus 1 is equal to m. Therefore, we are getting finally 2m plus 1. That means when we divide it by 2, we get the remainder as 1. That is, a is equal to 6q plus 3 is an odd integer. So second part also we have proved. So 6q plus 3 is also an positive odd integer. When r is equal to 4, a is equal to 6q plus 4. Overall, we can take 2 as common. So 3q plus 2, that is, we can write it as 2m. So 2m plus 0 or 2m, both means the same. And here let m is equal to, or let 3q plus 2 is equal to m. It is an even integer as we are keeping remainder as 0. The next step, the last step, when r is equal to 5. So a is equal to 6q plus 5. We can split this 5 as 4 plus 1. Isn't it? Same way, we are combining 6q plus 4, that is taking 2 as common. So when we take 2 as common, it will be 3q plus 2 plus 1. And now we are assuming 3q plus 2 as m. The next step, it will be 2m plus 1. That is, when we divide by 2, the remainder will be 1. That means a is equal to 6q plus 5 is an odd integer. So 6q plus 5 is an odd integer. That also we have proved. So therefore, the odd integers are of form 6q plus 2, 6q plus 1, 6q plus 3, and 6q plus 5. Let me know if any doubts in the comment section. I'll try to clarify. The next video, we'll try to complete this exercise. And I hope this will be a useful video for you all. Thank you. Take care.